This is the chapter that will give lots of people trouble. And my biggest suggestion to you is to go back and do the homeworks. And more importantly, do the homeworks kind of out of order, because a lot of people can't recognize the difference between p and y bar and p hat and mu. Be able to recognize these symbols that we talked about earlier, which p hat is the sample proportion, p is the true proportion, y bar is the sample mean, and mu is the true mean. So be able to understand when we use these symbols, why we use these symbols, what conditions go along with these symbols, and be able to keep everything straight. Because I think the hardest part for a lot of people in this chapter is reading the problem and understanding what symbols we're using. And every time you read the problem, this is my biggest advice to you, read over the practice test. And when you see a problem like this, write down the notation from it. Don't start flipping to the formula sheet right away. First, identify the notation in the problem. I've seen so many people use the wrong formulas or come up to me and say, there's no P in this problem. There's no P hat or there's no sigma. And they're right, I think. Oftentimes they tell me about a problem that they can't do because they're trying to use the wrong formula. So first things first, identify what the problem is. That'll also make sure you're using the right conditions. So let's get started here. A discrete random variable is a number that can only take on whole numbers, where we have discrete versus continuous. Discrete random variables are like number of goals in a soccer game or number of people who believe in ghosts. So discrete random variables would have to be like 5 people believe in ghosts. So that's a discrete random variable. Next, we have probability distributions and probability mass functions. So probability distribution is what we're going to really deal with in this chapter. A probability distribution is the idea of something theoretical. It's like if 20% of UT students smoke, we can come up with the theoretical distribution of what would happen if we go out and sample 100 students. And that's what we're going to compose, at least for the first part of this chapter, till we change it around to quantitative. We are coming up with a probability distribution that is made for sampling. So when you think about it, we have a probability distribution that gives us what could happen when we go out and sample. This goes along with the probability mass function that we've already created previously. Just a little while ago, we created this probability mass function here of flipping a coin and getting heads, a certain amount. We have the discrete random variable x, which would be 0, 1, or 2 heads, and we have the probability of that event, which would be 25, 50, and 25%. So this is a probability mass function right here, and we have the discrete random event, the number of heads we get. So a lot of this information is similar to 12. It's the general idea, and now we're bringing it in a new direction. So now, we have what does it mean for trials to be independent? That means one trial will not influence the next trial. And this is very important, especially in sampling. You want to randomly sample and you'd want to have each of your trials be independent of the last. So we can build, especially with known probabilities. There's a great example in this with rolling a dice and we think someone's using a loaded die. And in it we find that we get 31 sixes out of 100 dice rolls. Now, if the dice is truly fair, we should get 1/6 dice rolls being 6. And that would be 16.6% of the time. Out of 100 dice rolls, that would be 16.6, which is not a discrete number, but still we can see that we're way over at 31. But we need to figure out how odd 31 is. So when you think about how trials would be independent with a dice roll, they are. Because each dice roll, if we pick it up and shake it, would be independent of the last. If I roll a 6, it's not going to make me roll a 6 the next time. So we do have independence in our trials. Know the difference between a population and a sample. Very important here, and this goes back to chapter 12. Populations are the truth, and it's everything. So for that dice, the true proportion, what we would expect from it, is for it to roll 6 1/6 of the time. And that's for the population of all dice rolls that dice will ever roll, and it's basically infinite. But then we have a sample, 100 dice rolls. So now we are looking at just 100 observations, and this would be p hat. The population of dice rolls, the truth for it, and what it will actually roll in the very, 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 very long run for what it would do is p. That is the true proportion of sixes it rolls. But we only understand the sample proportion. When we look at what a sampling distribution is, it is what could happen when we roll that dice 100 times. And let's go ahead and formulate this now. So if this dice is supposed to roll 6 1/6 of the time, that would be the true proportion. We can go ahead and enter that in as the mean because that's what we expect to see. So the mean of the sampling distribution of p hat is 1/6. Now we need to find the standard deviation. The standard deviation is found by the formula p times q over n square root. And we simply type in, let's clear the calculator, 1/6 times the complement of 1/6. So remember, something plus its complement equals 1. If you look at the two numbers I have right there, they equal up to 1. And then we divide by our sample size, p times q over n square root, and we square root it. I suggest doing that on your calculator in steps. Do p times q, then hit divide by 100, then hit enter, and then do square root, second answer, or you could retype it in. But do it in steps. Don't try to write the whole thing into the TI calculator at once. Just do it in parts. This is our standard deviation, and this is for a sample size of 100. Very important. This is not for just any time we roll the dice, because that n could change. We could do it, what if we did it 200 times or 300 times? The distribution would get tighter. And this is what we could theoretically see. If you look at what the values are on here, the most likely thing is 16.6%. The things that are not so likely are things up towards 27%, 27.8%, or things as low as 5.4%. Those are not likely because they are 3 standard deviations away. We can find the z-score for anything by just figuring out how many standard deviations it is away. So let's figure out how far away 31% is. So we have the standard deviation here. We take observation because when we rolled that dice, we observed 31 out of 100 sixes. So that is 31%, 31 divided by 100. We do observation minus mean, put in one more 6, divided by standard deviation. Observation minus mean over standard deviation. It's the same sort of formula we've been using. This time the observation is p hat, the mean is p, and the standard deviation is p times q over n square root. If you notice, if we were to go up another standard deviation, that's right about where 31 would be. Just look at how it's going. You can't see all the way over here, but right over there is about where 31 would be, and that's 3.847 standard deviations above the mean, and that is pretty odd. That is more standard deviations away from the mean than we would normally expect something to fall. And we could pick up another dice in our casino, and it could roll 17%. And let's see, if we did it 100 times, this is very important. This isn't like rolling it 50 times and you get 17%. This is what we expect when we roll it 100 times. We expect to see results in here somewhere. If we roll it 100 times, this is what the sampling distribution looks like of what we should see from samples of 100. So with this in mind right here, you can see, and I don't even need to solve for the z-score, but 17 would be very close. It's going to be right in here somewhere. So very, very small. We could find out the exact z-score if we want. 0.17 minus 0.16666 and divide by, there we go. As you can tell, it's so very, very close that this is obviously what we expect. You can't get 16.6, and you can get 17. I could get 16, but this dice landed exactly where we expected it to land, almost exactly. It's best as we could since it has to be a discrete number. So with this in mind, once again, what we're doing here is so very important. This distribution is what happens after we do many, 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 many trials of 100 rolls of the dice and we see what the sample proportion is. It's built that way, as in there's lots of results in here that would happen and very few results over here. It's just theoretical. So that should give you an idea of what this distribution is used for. And once again, this is for categorical data right here. It is when we have something that's like yes, no, did I roll a 6? Did I not roll a 6? That's yes, no, categorical data. So we talked about how to find the mean and standard deviation. The mean and standard deviation were found by the mean being p and the standard deviation being p times q over n square root. Don't accidentally use p hat there. P is the true proportion, and that is what you use in the formulas because it's the truth. Know when the shape of the sampling distribution is approximately normal, and it must meet 3 conditions. The 3 conditions are the data must be randomly selected. We must meet the success-failure condition, which means NP and NQ are both greater than or equal to 10, and that is expected number of successes and expected number of failures. Remember, just do the formulas. NP, greater than or equal to 10, NQ, greater than or equal to 10. And in our previous example, we can check it because the dice was supposed to roll 6 1/6 of the time. So out of 100 dice rolls, we expected 16.66666 sixes. I was going crazy right there. And then we expected how many not 6s? Well, here is Q. You can do 1 minus P to get Q. And now, out of 100 dice rolls, we expect 83.33333 not 6s. So we meet the condition right here. And I didn't use 31% because that is P hat. That we would not use 31% there. We use 1/6 because that is P. That is the true proportion we expect to see. So as long as both of those are greater than or equal to 10. Finally, we have the 10% condition. The 10% condition is we have to sample less than 10% of the population. A long reason why, and there's lots of articles, but just remember, we need to sample less than 10% of the population. And lucky for us, dice rolls are infinite, so we could not have sampled more than 10%. So the 3 conditions: random. Make sure the question says random. If it says random, say the question said random. If it doesn't say random, then say the question did not say that the selection was random. Next, we have 10% condition. 10% condition, we sampled less than 10% of the population. And finally, success-failure condition. And this applies to categorical data, because categorical data is you have this many successes and this many failures. Make sure if you say this condition, it's categorical data, which means you'll have P and P hat and all that good stuff right there. Next, be able to use the 68, 95, 99.7% rule to find the approximate probability of a specific P hat or greater or less from a normally distributed sampling distribution of P hat. So let's take a look at some of this. Going back to our dice example right here, we talked about what might be odd. And let's say we were to get 21%. Now, if we had 21 out of 100, that would be 21%, and this is just number of successes in our sample over sample size. This formula is often called x over n equals p hat, but just make sure you remember number of successes in the sample over sample size is equal to the proportion of successes in the sample, which is sample proportion. So we can do some estimating right here. If we did above 21%, because we saw 21 successes in our sample, let's guesstimate what that might be. According to the empirical rule, 68% is between here. If there's 68% inside, there's 32 total outside of it. With 32 outside, that leaves 16% above one standard deviation. This would have to be less than 16% because 16% starts right here. Right here we have 95 between here and here. That leaves 5% total outside in the two tails and 2.5 in one of the tails. So this area right here has to be between 2.5 and 16 because 2.5 is too little and 16 is too big. The next mark right here would be 50%, but we're not even worried about that. This goes back to your Chapter 5 stuff, and you can go back and review it, but this is some review concepts. That looks to be at about, is it 1 point, I don't know, I'm trying to make a really good guess right here. It's between 2.5 and 16%. I say it's about 11%. Let's take a look. It's 11.89%, And we would just want you to use the empirical rule, but I always like to take a guess. And the guess turned out to be pretty close. That's the really great thing about doing this. Try to use the empirical rule to figure out the percent. Also, we can ask you if things are odd. And this would not be odd because it's between 1 and 2 standard deviations above the mean, and that's not a very big z-score. So now we move on to quantitative data. And the conditions are going to stay basically the same, but we have new symbols here. We have y bar and mu. Y bar is the sample mean, and mu is the true mean. So this is the same idea, but with a different type of data. Because now when we build the distribution, we're going to talk about what could happen when we go out and sample quantitative data, the y bars we might observe given some mean is true. Because we know what the true mean is, and now we are seeing what is possible in a sample of size n for different y bars. The central limit theorem is key to this chapter. The central limit theorem states two things: that the distribution of the sample mean of size n will get more normal and tighter as n increases. So two things happen to this distribution. As n increases, it gets more normal and more tighter. Let's put this to the distribution of sample means of size 2. This is the original distribution right here. We are going to make a new distribution of means where we are averaging together 2 points. Take a look. We take 2 points, we average them. 2 points, we average them. 2 points, we average them. And we keep doing that. And we keep building the distribution. And look at what we get as we keep doing it. This is the theoretical distribution of the mean of sample size 2. As in, we get every blue point by taking 2 black points and averaging them together. Because it's rare, is it likely you'll get 2 points from all the way down here? To get a blue point all the way down here, you have to get 2 black points down here. And that's not going to happen very often. It could happen. I haven't seen it happen, but it's more likely we'll get something towards the middle because, well, we might get something here, and it'll average out. A lot of things are going to average out. The things on the far side, you really have to get a point here and a point here to get something all the way down here. And interestingly enough, you'll notice the mean of this distribution, if I keep hitting enter, and it finally worked for those watching it, the mean of this distribution down here is the mean of the original distribution. Just like the true proportion is the mean for the distribution of the sample proportion. The true mean will be the mean for the distribution of sample means of whatever n is. So it's pretty easy right here because it's not going to change. It's like this. If one guy is 5'10", what would you expect one guy's height to be if I go out and talk to him? You'd say 5'10". It's probably the best guess. But if we went out and talked to 20 guys and we averaged their heights together, what do you think the average of 20 guys' heights would be? You'd probably say 5'10", because, that's what most guys are. So it would average out. And also think about it. If you were to average together 20 guys' heights, you'd probably get some, if you did it randomly, you'd get some taller, some shorter, and you'd probably be likely to find something closer to 5'10". But you could, if you talk to one guy, find something far away. But the whole idea of averaging together more is going to make the distribution tighter. And you can see this happen when I put it all the way up to 25. And now every single blue point is 25 black points. So to find one blue point, we have to average 25 black points. And you'll notice all the blue points are going to be a lot tighter this time. So it gets tighter and more normal. You'll notice the last one looked like a pyramid, which is not a true normal curve, while this one looks like a normal curve and is tighter. The standard deviation went down. If you take 9.52 and divide it by the square root of 25, let's take a look at that. 9.52 divided by 5, which is the square root of 25, we get 1.9. And it might happen that goes to 1.90, which it would round down to. I'm doing a whole bunch more simulation. It finally did it. Oh, it went back up. It's so close to 1.91, but I really want to stay at 1.90 because that's more true. But more simulation gives better results. And if you notice, that my calculations rounded to 1.90, and by simulating more, this is all simulation. It's not meant to turn out exact. It does because it's the central limit theorem, which when we increase the sample size for the distribution of means, the distribution of sample means gets tighter and more normal the larger n gets. An important thing to know here is that if the distribution is really skewed, sometimes it can take sample sizes larger than 25. And this one does all right. I've created myself some custom ones where you would need something a lot larger. Let's make a really, really skewed one in here. We're just taking, and this is really skewed. So if you notice, you can still see a little bit of the skew. So sometimes extremely skewed distributions need sample sizes higher than 100. So the less normal it is, the bigger n it needs. If we were to do the distributions of mean and sample size 2, this doesn't look normal at all. So the less normal it is, the bigger n is needed. But what about if we have something normal? How will the distribution of means of sample size 2 look? And the answer is normal. Because it's just going to look more normal and more tighter, but it already looked normal. You have to take into account the way the parent population looked. If the original distribution is highly skewed, you sometimes need a distribution of means of sample size 100. 25 works for most. As you saw, I put it to 25 and it worked for most until I put in that really, really skewed distribution. If it's normal, well then it doesn't need to be more normal. There's no such, once it's normal, more normal just means normal. So it'll stay normal. And you notice that right here. I can probably make some of the bumps go away and make it look really perfect if I keep simulating more results. But it looks great. And this is the central limit theorem. Once again, as we increase n, the distribution becomes more normal, and also the distribution becomes tighter by a factor of the square root of n. You can check the math here. The original standard deviation is 5, and we need to divide 5 by the square root of 2. So let's take the square root of 2 and copy that, and do 5 divided by the square root of 2, and it's 3.5, and that rounds to 4, 3.54. Good stuff right here. So we have the conditions for the central limit theorem to know if we can actually use this right here. We need to make sure that we have collected this randomly, that we're randomly collecting individuals. Like I said, when you talk to these people about their heights, and remember this is quantitative data because I'm asking them about heights, so it would be randomly selected individuals. Next, we need to pass the 10% condition. Less than 10% of the population has been sampled. I spoke to less than 10% of guys in the population. Finally, we have the large enough sample condition. And I sometimes call this the large enough n condition, because if we have a large enough n, we can use the normal curve. And that's the key to this right here. So this is when we can use it. If we have a very skewed distribution, n needs to be closer to 100. And in most cases, if the distribution has just skew or it's uniform like we saw, nothing too crazy, 25 is large enough. So knowing the difference between the distributions we have right here, we have a sampling distribution that we've been using in these problems. Real world, you see histograms, and that's what we usually get. But now we're talking about a theoretical distribution that's made up of either p hats or y bars, because it's what could theoretically happen if we were to go out and sample a sample size of n. And once again, these distributions are based on what would happen after you get tons of y bars, tons of p hats. You go out and sample a whole bunch, and this is what you would see in the probability of seeing those things. So let's go ahead and calculate the mean and standard deviation. Here we are back using the David M. Lane applet, and we can do some calculations on this again. Now you'll notice what I've put in here is that we have the distribution of individual guys' heights, where one guy is 70 inches tall and there's a standard deviation of 3. So someone who is 76 inches tall or 6'4" would be 2 standard deviations above the mean. But now, if we were to go out and talk to 25 guys and average their heights together, what would we expect to see? So this becomes a theoretical distribution of the sample mean of size 25. Now, once again, we would not see the mean change because we would still expect the average height of 25 guys to be 70 inches. But what changes is the distribution becomes more normal. And maybe this distribution was normal to begin with, so the distribution of means will still be normal. And also, the distribution gets tighter by a factor of the square root of n. So here you see that standard deviation was 3, so we need to divide 3 by the square root of 25. which is 3 divided by 5. And we take here and we have 0.6. So now you see a whole new distribution here. This is the distribution of sample means of size 25. And it would be very odd to find that if we talked to 25 random guys that they were 6 feet tall on average. And you'll notice here, because 6 feet is, I believe, 3.33 standard deviations above, and you can use the same formula again. You could say observation, which is 72 inches, minus mean, divided by standard deviation. And observation minus mean over standard deviation just gives us the z-score. So once again, we're just doing y bar minus mu over our new standard deviation, which is 0.6. Very important here. Once again, a lot of people make mistakes on these problems because they don't realize you're using the new standard deviation for a mean of sample size 25. And you think about when stuff like this would be used. We could talk about weights on an elevator. If you think about how an elevator is used, it might say maximum capacity 10 individuals. And so they could worry about the average weight of 10 individuals and if that would go over. If you think about things like a parachute, parachutes are meant to be used by one person. So we wouldn't worry about the failure rate or we wouldn't worry about the strength of 25 parachutes on average, because maybe a parachute can support so much weight being pulled on it. And if you think about it, if you average together a whole bunch of parachutes, you'll have some bad, some good, and probably they'll all generally be pretty good. But when you're in the air, do you care that most parachutes are pretty good, like on average parachutes are good, or do you care about your parachute is good? And when you think about how something is used, the distribution of single observations, which is not being shown here, would be better for parachutes. When you think about elevators, the distribution of sample means, like we'd say what could theoretically happen when 10 people get on that elevator, would be better for that. And we could make decisions about, how many people should be on this elevator if we talk about the theoretical distribution of sample size n. What would happen if 10 random people got on this elevator? And of course, there is a slight problem with independence right there. People travel in groups. And so you might say, well, maybe we have some problems here. Maybe we should be a little bit more careful and maybe take a person or two. Because every time an elevator probably says max capacity 12 people, it could probably handle 15. And I think we've all probably broken those rules. Not me, of course. So anyways, yes, knowing when to use these distributions. My biggest suggestion to you is try to keep them straight. The last one we did here is quantitative data, knowing when to use certain conditions. If it is categorical, the third condition is success failure. If it is quantitative, the third condition is the large enough n condition. So make sure to keep that straight. Look at the question, figure out what it's asking, and then write down the notation. Practice, 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 because these problems are the ones people have a lot of trouble on, and I see them blank. Don't let that be you. And good luck.